Hi, everyone. No, we're just about to hit the top of the hour. We'll probably wait about a minute after to let more people in the room, and then we'll get started here. All right, looks like we're about a minute in. While I wait for more attendees to join, I'll just start with some housekeeping here. Thank you everyone for joining today. We're really excited to start this webinar. Just a few things. This will be recorded and the recording and the slides will be distributed by the end of the week. So please look in your inbox for that. If you have any questions, feel free to drop them in the chat or hold on to them till the end. If you just hit that raise your hand button, we'll let you come off of mute so you can ask your question if you prefer. Other than that, I will hand over the presentation to Malin and we'll get started.
Thanks, Kate. Okay, hoping everyone can see my screen, right?
Yep, looks good.
Perfect. So thank you all for joining. My name is Madeline Talebi. I'm an energy engineer with ICF, and I'll be presenting one of the studies that was done through the program on gas absorption heat pump. This is number one. We're doing a couple, so this is the performance mapping, and this is with hydrogen blending. And before getting started, just want to acknowledge all the project collaborators for this effort. So those from ICF, and then all those from GTA Energy. I think we might have one or two currently on the call as well. So, but yeah, just did the laboratory study with GTA Energy for this effort. So brief agenda, I'll touch on a little bit on how GHPs, why we're interested in them in California specifically. We'll touch on a little bit on hydrogen fuel blending, talk about some objectives, and then we'll get into kind of the bulk of the presentation, covering the test plan, the steady state performance mapping, data, experimental data, and then the load-based performance experimental data, kind of the two parts of the lab test. And then I'll talk about, briefly touch on the Energy Plus modeling development and then recommendations moving forward. So I mentioned that this is the GHP number one. So the unit that was done for this study was the Rober GHP-A unit I have pictured here. And if any of you have been on previous calls for the public disseminations, like I said, there was a previous project that was only natural gas, 100%. It was a more a thorough test matrix. So that report is publicly available if you'd like to look through it, if you're curious more about what happened with the natural gas side, as I'll just be talking about, mostly talking about the hydrogen blending side of the testing. And so if we look at California on emissions control, so why we're interested, so if we look at water heating, it is the largest non-industrial end use of natural gas in California. And I've gone ahead and broken down natural gas consumption according to by end use. And then this is covering the three sectors, the industrial, commercial, and residential. So as you can see, industrial has the largest impact. However, commercial and residential still have quite a significant impact in that space and where there could be lower consumption possibilities. And I listed a few California bills and legislation that would not only lead us to want to, kind of decarbonize or lower natural gas consumption in California, along with why we're interested in the focus sector of that being multifamily or commercial, to kind of spearhead some of this effort, and why we would want to incorporate this into a multifamily sector specifically. So I won't go into the details of these bills and legislation, but if you're interested in looking more into them, I have them listed here. And so when we talk about hydrogen blending, I don't want to make any assumptions. So I'm going to say in terms of, if I say a hydrogen blend of 5%, that means that it's 5% hydrogen and the balance 95% is going to be natural gas. And so when we look at, there is some hydrogen blending research going on, specifically in California or Southern California. And there are some limitations with regards to hydrogen blending, primarily associated with the cost. There's several ways that you can uh, somewhat harvest your hydrogen or generate your hydrogen or extract it, and some are more costly than others. But that research is definitely ongoing as we're kind of looking more towards hydrogen as a feasible fuel option or fuel sub. And so I listed here some on-site max hydrogen blending across various regions just to kind of give some insight into where the world is in this level of research. So the US excluding Hawaii is at a max blend of 5%. The Hawaii only is at 15, Canada's at 5, Europe's at 20, kind of the leader in this effort, and Australia's at 5. This is from a CPUC or California Public Utility Commission from 2022, so this might very well have been updated. But all this to say that Europe is definitely the leader in this effort. And through the GET program, we've actually done a study, one of the earlier studies in the program, kind of looking at hydrogen readiness labeling, specifically in the European market. And so that if you're interested in kind of where that study went, that's also available on the website. And so getting into the objectives, ultimately we want to improve well uptake at the sector level. So as I mentioned, that's going to be the commercial sector. And we want to improve well uptake at the technology level, so specifically in the GHP space. And so if we look at the technology performance, looking at in a controlled environment, and as I mentioned, it's really two components of that laboratory study, so the steady state performance and the part load or transient performance testing. And then ultimately, we want to look at how emissions will be evaluated with the various hydrogen fuel blends. And then finally, looking at developing performance mapping curves that will ultimately be contributed towards the Energy Plus GHP module. And so I'll briefly touch on the equipment commissioning and test plan for this. So again, it's the Rover GHP-A system. So I've listed some of the commissioning tolerances that were used. So anything that's the rate, so the flow rate, the firing rate, and the heating output are about plus minus 2%. And then any of the temperatures, so the outside air, the return, and the supply, plus minus 1 degree Fahrenheit. And following that the commissioning of the system, everything was in good agreement with what the manufacturer had intended. And then for the steady state testing, so as I mentioned, there was a pretty thorough testing that was done for the natural gas. Given time and resources, this was limited or pared down to really hone in on where we might be able to see some, varying in trends, or where the kind of the meat of the testing for the natural gas was the most interesting. So this was pared down to looking at one flow rate of propylene glycol at 13.6 GPM, an outside air temperature range from 17 to 90 degrees Fahrenheit, so 5 points within that range. One return temperature at 110 degrees Fahrenheit. Propylene glycol was kept at a constant 35 volume percentage, and then the hydrogen blend was between 0 and 30%. So essentially looking at 4 points. So the 0% was volume percent was mainly for the emissions, and then the 10, 20, and 30 were for the emissions and all of the steady state and transient testing. And so for that transient testing, everything was kept constant, same as steady state, just adding that time factor. So the on runtime of the cycle, and that's at full fire, it was between 0.1 and 0.7 hours, so 5 points within that range. And the off time was about 30 minutes, just one test point for the off time. And then just wanted to highlight this. the hydrogen blend test setup. So there are multiple ways that you could go about, mixing your fuel as we're doing a blend for this study. So I have the first one listed here. So the original plan was to take 100% hydrogen with natural gas and use a mass flow controller and essentially manually blend it through a single feed. But just given time constraints, GTI decided to look at just buying tanks that were pre-blended, so looking at the 10, 20, and 30%. But yeah, just wanted to highlight this point on the hydrogen blend test setup. And so getting into the results. So for the steady state results, there's this graph I have here. So hydrogen 2 this is the hydrogen percentage thermal input. So if we look from left to right, this is the outdoor air temperature. And I have the natural gas, 100% natural gas, and then 10, 20, and 30% blends. So just focusing on the x-axis from left to right, as you can see, the outdoor air temperature is increasing, and that is causing a decrease in thermal input as you go from left to right. And then as you can see here, if you look from top to bottom for the thermal input, at natural gas, the curve on the top, it's going to be at the highest thermal input, and as you go down and increase your hydrogen blend percentage, you'll be decreasing your thermal input. And so if we look at the decrease in thermal input with respect to the outdoor air temperature, that can essentially be attributed to density fluctuations given the outside environment. And then if we look at the increasing hydrogen blend percentage and why that's causing a lower thermal input, it's because your high heating value is decreasing. And so one way to essentially look at gas equivalency is to use the WOB index or the WOB index. I never quite know how to pronounce this one, but the WI essentially, and it denotes gas replacement equivalency. So that's accounting for both the high heating value, as you see on the x-axis, and that is over the square root of the density. So attributing or factoring in the outside air temperature density fluctuations. And so what this essentially says is if we look at the 30% hydrogen blend, this is essentially pointing out that that's at a gas equivalency of 92% of natural gas. So it's important that we both factor in the high heating value and the density because we don't want to lose any of those correlations that we see with the thermal input graph. And then just highlighting the power input comparison. So if the electricity or the kilowatts are actually being a contributing factor in the overall COP. So just wanted to highlight this. As you see, the power input has minimal impact, and you might see COP as both gas consumption and power consumption or electric consumption. But for the case of this study, I'm only going to show the COP gas only, given that the power input has minimal impact. And if you were wondering where the power input is mainly coming from, it's coming from the circulating pump and the fan components of the system. But again, for moving forward, I'm just going to show the COP gas only. In the full report, we have both the gas only and the gas plus electric listed, but the differences are negligible. So before getting into the COP, just wanted to show the normalized thermal output ratio. So this is respect to the thermal input. And as you can see, there's very close alignment or close overlap between the 100% natural gas, the 10%, the 20%, and the 30% hydrogen blends. And so ultimately, when we did the natural gas testing, this was graphed according to what the manufacturer had published. But since we're seeing close alignment with the hydrogen blend, there's really virtually negligible difference between what the manufacturer has published for natural gas, what was the testing said for natural gas, and then what we're seeing for 10, 20, and 30%. And so how that translates to COP is that, again, there's also a close overlap amongst the different blends, and then looking at how that compares to the natural gas, 100% natural gas. And so virtually the system performance is not affected or minimally affected by hydrogen blending, which was definitely a positive trend to see. And then if we look at how this affects emissions, this was somewhat of an interesting revelation in the study. I think when you're blending hydrogen, and especially as you increase your hydrogen blend percentage, there's always the risk of increasing your thermal NOx. But in this case, the NOx actually decreased, and combustion pollutant carbon monoxide formation decreased as well as we increased the hydrogen blend percentage. So that was an interesting finding. And then if we look at more favorable combustion products, so carbon dioxide and oxygen, carbon dioxide decreased with the increasing hydrogen blend percentage, and it was essentially in favor of more oxygen-rich environment or more oxygen formation, as you can see from the blue bar curve that increased. And then getting into the load-based or the transient results. So we want to take a look at the steady state experimental data. That's essentially taking the steady state, taking a snapshot of that, and essentially setting that as the max capacity when calculating the part load percentage, just to take all of the laboratory study and calculate an accurate part load percentage. So the COP ratio, or essentially otherwise known as the D rate, is the efficiency relative to the load. And so as you can see, the natural gas curve that's listed here, so this was actually developed using a least squares method from the previous study. And so taking that same curve or that same linear, or I guess not linear, it's more of a logarithmic behavior, but taking that same curve and overlapping it with the 10, 20, and 30% hydrogen blends, there's a close alignment. And I think that's more or less what we would have expected given the close alignment with the COP just from the steady state across the 10, 20, and 30% with 100% natural gas. So I'll briefly touch on the Energy Plus modeling. So objectives overall are to forecast energy consumption, utility bills, and greenhouse gas emissions. Target audience could really be anybody that's interested, but to hone in on folks that might be more interested as the California policymakers, program and mechanical system designers, software developers, and of course manufacturers. So I have a lot of parameters listed here, so I'll kind of take this slide line by line. So essentially, each of individual modeling parameter was developed and plotted with the experimental data. So essentially the model data versus the measured data, and I'll show how that error kind of compares with one another in the next slide. But it's essentially predicted within plus minus 5%. And so I just listed some of the key parameters. They've been slightly simplified here, but in case you're interested in kind of where this is coming from. I didn't just want to say, modeling parameters without at least listing what this was referring to. So that being the heating capacity and gas use and all of the parameters that kind of coincide with what these two kind of encapsulate. So this is outlined in more detail in the full report, but again, just wanted to touch on which modeling parameters I'm referring to and kind of how those were developed or where they came from. And so as I mentioned, the parameter error between the measured and model data was about plus minus 5%. And I have this red bar highlighted on the 0% axis. And you can see anything that hovers above and below is estimated at about plus minus 5%. And then if we look at the overall modeling accuracy based on the COP, and again, only the gas alone, the error comparison between the measured and model data is approximately plus minus 5%, and that's above where I've drawn this dashed line with the arrows above a part load ratio of about 25%. As you can see on the bottom, it kind of increases slightly, but nothing that's of too much concern. I think if you wanted to get a narrower window, you might increase your testing averages or so forth. And so just to summarize some key takeaways, so the Rober GHPA, it closely aligns with the manufacturer's published data and is minimally affected by the increase in hydrogen blend percentage. And we see significant emissions benefits. Again, we were expecting, as you would expect with increasing hydrogen, just based on available research, you would expect more or less an increase in thermal NOx, and that happened to not be the case. We saw instead an increased formation of oxygen and decrease in CO2. And the performance of the GHP at part loads is mostly independent of the fuel supply, so meaning the hydrogen blend percentage. And we're seeing an overall modeling accuracy for those performance mapping curves in the Energy Plus of about plus minus 5 to 10%. And then for future studies, definitely look at additional market-ready GHP experimental testing that's currently ongoing, and hopefully look towards a user-friendly tool development that hones in on GHP research. And that's all I have on my end. I'll take any questions.
Very good, Madeline. Any questions from the audience about GHAP lab testing or modeling? Oh,
I
there is
see
one
one.
question in the chat. You see that?
Yeah, I'm not too sure on how to answer that.
I could take a swag at it. Certainly, potentially, gas heat pumps and other technologies might work as a complement to electric or electrification in particular areas. But this is primarily a gas technology as opposed to other technologies that are sort of hybrid that might switch between gas and electric or pure electric heat pump technologies. I don't know if that answered the question or not.
I see Christopher's question. As far as I'm aware of, I don't believe that was an issue for GTI, but I think Lee is on the call. He might be better able to speak to that, or I thought I saw him, maybe. I don't see him, but yeah, that was not communicated to me as far as any issues regarding
We had a little bit of discussion yesterday about testing issues. I think, Christopher, I know where you're
yeah,
coming from, and I think there was a separate issue, but it wasn't related to the firing. But in the lab testing, it was calibrated at the beginning of the first test, right?
yeah, I that was my understanding. I think, oh, here we go. I can allow Lee to talk.
Sure. So, sorry for that. I
No,
guess
that,
the
yeah.
question is, how does the cost of a GAHP compare with an electric air source heat pump? I'm not sure all the exact prices, and it depends if you're looking at a comparison with a complete air conditioner or just the GAHP. The particular focus seems to be a good application for hot water where higher efficiencies are obtained, COPs of 1.2 to 1.3 to 1.4, while still not requiring additional electrical capacity. Does that answer the question? Thanks.
And Steve had a second question.
I think Madeline
Yeah,
or Stephen, you can answer that better than me. Yes.
Yeah, I
I,
can.
from my understanding, I know there are several ongoing measure packages that are being looked at the moment. Yeah, Stephen, do you have any more insight for incentives?
Yeah, pretty much the same thing. SoCal Gas is the one working on those measure packages or responsible for them. So I don't know if they're currently offered, but I know they are looking into deploying them. So I would probably check on the SoCal Gas website, or if someone here on SoCal Gas knows it, let us know. Did the three of us address all the questions that are posed? Or are there any other questions? Madeline, you see Christopher's question?
Yes. Yeah, as far as my understanding, I don't believe there were any issues with it reaching full fire, especially because when the cycle was on, it was at full fire. Does that kind of echo your sentiment as well?
Fair question. Yeah, the unit performed very much in line with the published data.
But
Thanks.
this is the unit that produces, I believe it's 123 kBTUH. Is that correct? It's not the other unit.
That is correct. Thank you, Stephen. There were two units that were testing in parallel, but this one was the 123. Correct.
Looks like Steve's and Christopher's questions are addressed. Anyone else, or do either of you have any follow-up questions? Give another few seconds if any questions come to mind. Not, Madeline, thank you for your presentation, and Lee for your backup, and I appreciate all the audience for attending today.
Thank you all.
Thank you.